Swayam Prabha. Digital India. Educated India.
Welcome to the class. Here we will see one example of regeneration which we had not seen yet. This example says that a steam power plant has steam with 90 bar and 500 degrees Celsius at the inlet of the turbine. Condenser temperature is 40 degrees Celsius. Plant produces power of 500 megawatt. It has a reheater placed at 18 bar which increases the steam temperature again to 500 degrees Celsius. At the reheater pressure, one feed water heater of drain cascade backward type receives the blade steam. The HP and LP turbines have 92 and 90% efficiencies respectively. Efficiency of pump is 75%. Find the steam flow rate in the turbine inlet, cycle efficiency and work ratio. Consider TTD to be 1.6 degree Celsius. Having said this, this example specifically is chosen for the fact that it deals with drain cascade backward type. So, let us plot the TS diagram for this example and number our usual notations. So, this is TS diagram, then we have 1 and then so here it is cascade backwards means steam is sent back to the lower pressure through throttling. So, we will put 1, 2 dash, but it is not the ideal pump, so it will be 2, and then similarly this is not the ideal turbine. So, we will have 3 here since it is 1.6 degrees Celsius extra. So, this is 4, this is 5 dash, this is 5 and this is 6, this is 7 dash and this is 7, then this is 8 and this is 9. And so, we have this as 90 bar, this suppose we will say Y mass of steam. So, this is 1 minus Y, 1 minus Y here, 1 here, and this is 18 bar. This is, it is told that it is 40 degree Celsius. So, if we see into the steam table and find out the saturation pressure corresponding to 40 degrees Celsius, and this it turns out to be 7.38 kPa. So, these are the given things with us. So, we can find out from steam table for this H1, and H1 is 167.57 kilojoule per kg. Similarly, we can find out at 18 bar what is H8. H8 is the saturation enthalpy of liquid, since it is told that the steam condenses there in the feed water heater, and then H8 at 18 bar liquid saturation enthalpy is 883.4 kilojoule per kg. Now, we can find out for H2 what is delta H for pump, and that delta H for pump is V1 into P2 minus P1. So, specific volume is 001,008, so into 90 into 100 minus 7.38. So we get delta H for pump, which is rather ideal, delta H for pump. So we will put dash, and this turns out to be 9.06 kilojoule per kg. So we have H2 is equal to H1 plus delta H dash P, but pump has efficiency, so it should be divided by pump efficiency. So it will be 167.57 plus 9.06 divided by pump efficiency is 75%. So we get it as 179.65 kilojoule per kg. Now we can find out T3. It is told that TTD is minus 1.6 degrees Celsius. So it means that the difference between this saturation temperature of feed water heater and the outlet temperature is minus 1.6. So it means that T3 is equal to T8 plus 1.6 degrees Celsius. So T3 happens to be 208.75 degrees Celsius, since T8 is 207.15. Having said this, we can go into the steam table and find out the enthalpy corresponding to 208.75 degrees Celsius, and then in that case we will get H3 is equal to 875 kilojoule per kg. We can as well find out this enthalpy from liquid tables, and then these enthalpies would almost be similar. So for that fact we have now H4, which is this, and we know it is 500 degrees Celsius. So for that H4 is equal to 3386.1. We will keep also noted S4, which is 6.6576. So we know that S5 dash is equal to S4. So we can get H4, okay, so H5 dash, and that H5 dash we will see at 18 bar what would be the value at which we will get the entropy as S4. So H5 dash for us will be 2915 kilojoule per kg. Similarly, we can see it for H6, which is at 18 bar and 500 degrees Celsius. So we have H6 is equal to 3469.8 kilojoule per kg. We will keep also noted S6, and then S6 will be equal to S7, and then from that fact we can find out S7 basically is equal to S7 dash, S1 plus X7 dash into SFG. Okay, so this gives us X7 dash, and the value of X7 dash is 0.899. So from that we can get H7 dash, which is equal to H1 plus X7 dash into HFG. So it is 167.57 plus 0.899 into 2406.7. So we have H7 dash is equal to 2331.7. Now we can find out basically H5, where we note that turbine efficiency is equal to actual work, which is H4 minus H5 divided by ideal work, which is H4 minus H5 dash, and this gives us hint to find out H5, which is turbine efficiency into H4 minus H5 dash, and then it will have minus sign, and then we will have plus H4. So H5 is equal to H4 minus turbine efficiency into H4 minus H5 dash. So we have H4 34, H4 for us is 3386.1 minus turbine efficiency. This is high pressure turbine, its efficiency is 92%, so it is 0.92 into 3386.1 minus H5 and H5 dash 2915, and this gives us 2952.688 kilojoule per kg. Similarly, we can find out H7 by knowing the fact using the same formula as H6 minus turbine work into H6 minus H7 dash. So we have H6, which is 3469.8 minus turbine efficiency for low pressure turbine efficiency is 90%, H6 is 3469.8 minus H7 dash is 2331.7. So we get H7 from here as 2445.51 kilojoule per kg. Having said this, we can move ahead and then we can find out basically the mass fraction Y using the energy balance. Here the energy balance would say that the mass Y is losing its enthalpy from 5 to 8, where 1 minus, here it is complete mass, 1 unit is gaining its enthalpy from 2 to 3. So we will write down as Y mass is losing its enthalpy from H5 to H8, and 1 unit of mass is gaining its enthalpy from 3 to 2. So we can write down Y is equal to H3 minus H2 divided by H5 minus H8. So it turns out to be Y is equal to 695.35. The numerator based delta H and denominator based delta H is 2068.6. So we will get Y as 0.338. So this is the mass fraction which is extracted for the process of drain cascade backward. So we can write down now turbine work. So turbine work is equal to H4 minus H5 plus 1 minus Y into H6 minus H7. So turbine work is basically equal to H4 minus H5 is 433.412, 1 minus 0.338, and then we have 3469.8 minus 2445.51, and then this basically is 680.12. So we have turbine work is equal to 1113.5 kilojoule per kg. We have pump work as H2 minus H1, so which is 179.65 minus 167.5, it gives us 12.08 kilojoule per kg. So we have net work is equal to WT minus WP, and that is equal to 1101.46 kilojoule per kg. Here we have Q in, which is heat input to the cycle, and that is H4 minus H3 plus 1 minus Y into H6 minus H5. Here heat is added into two phases, H4 minus H3, this heat is added in the boiler, and H5 H6 minus H5 heat is added in the reheater. So we can keep all these numbers. So Q in is equal to 3386.1 minus 875 plus 1 minus 0.338 into H6 is equal to 3469.8 minus 2952.6, and this gives us Q in is equal to 2854.3 kilojoule per kg. And then we can find out from here efficiency, which is equal to W net upon Q in. So efficiency W net we have found out, which is 1101.46, Q in we found out 2854.3. This gives us efficiency as 39%. Work ratio RW is equal to W net upon WT. So we have W net as 1101.46, and turbine work is 11113.5, and then this gives us 989 as the work ratio. So we have to keep this point in mind. So we will have to solve this example of drain cascade backward, specifically for the concept that we are putting the steam blade which is taken out exactly back to the condenser or maybe to the lower pressure feed water heater. So we end the example over here. So we will go ahead with the next example. This example says that a cogeneration plant produces 5.6 megawatt and also supports 1.163 megawatt heating load. So this is the work produced and this is the heat load. We have to understand that this is a cogeneration plant. Here steam expands from 40 bar and 500 degrees Celsius to 0.06 bar. Heating load is supplied by extracting steam from at 2 bar, which condenses at same pressure till saturation liquid state. Find steam generation capacity of boiler, burning rate of coal if calorific value is 25 megajoule per kg, burning efficiency is 88%, and also a rate of flow of cooling water in condenser if its temperature rises 6 degree Celsius. This example for cogeneration is nothing but the example for Rankine cycle. This example is similar to the one what we work for the regeneration case, where we have some steam extracted from the turbine at certain pressure and given to heat the water in the economizer. But here instead of heating the water, this steam is used to heat the components or heat the product or heat in the processes. So this heat from the steam is used for the other purpose. So that is what this plant produces electricity through turbine and also gives the hot steam as a heat source. So we can go ahead and then plot the TS diagram. Our TS diagram says this. So this is 1, this is 2, this is 3, and this is 4, this is 5, this is 6 and this is 7. We know this is 40 bar, this is, we are bleeding steam m dot b. Here we say that there is m dot amount of mass, and so here is m dot minus m dot b, and here also m dot minus m dot b, and this bleed is taken at 2 bar. Here it is 0.06 bar, and pressure, we know this temperature is 500 degrees Celsius. So this data is given to us. With this data we will go ahead and find out different corner properties. First we will note H1 corresponding to 0.06 bar, or we can first find out H3 so that we can find out different flow rates. So for that let us denote H3, and H3 is found out at 40 bar and 500 degrees Celsius in the superheated part of the steam table, and this gives us 3445.3 kilojoule per kg. We will also note S3 at the same time such that we would have equated it for the other corners of the cycle. So S3 is equal to 7.0910 kilojoule per kg Kelvin. We know that S3 is equal to S4, and this gives us X4, and X4 happens to be in superheated part, or X4 happens exactly on the practically on the liquid saturation line, and so we have basically S4 is equal S4 is equal to 7.091, and this gives us H4 is equal to Hg at 2 bar, and this value is 2706.7 kilojoule per kg. So knowing this, we can further go ahead and then find out what is the heat given. So for that we should know H6, and H6 is liquid saturation enthalpy corresponding to 2 bar, and value of H6 is equal to, we can go ahead and find out the mass flow rate of the bleed steam, since we know that H4 minus H6 is given as a heat load. So it is completely HFG, and that we should know at 2 bar, and then that is m dot b, mass of bled steam, into HFG. This is given to act for the heat load, and that heat load is 1.163 megawatt, and then we can take it as into 10 to the power 3 kilowatt. So we know HFG, and HFG at 2 bar is equal to 2201.9 kilojoule per kg. So we can get m dot b is equal to 1163 divided by 2201.9, and this gives us m dot b as 0.528 kg per second. We can also find out m dot b in terms of kg per hour, so it will be 1901.4, which is kg per hour. We can convert it into the tons per hour as well. Having said this, we can then find out S4 is equal to S5. So this gives us X basically 5, since we know S5 is equal to S1 plus X5 into SFG at 0.06 bar, and we get X5 is equal to 0.84. So we can know H5 is equal to H1 plus X5 into HFG, and then that gives us H5 as 149.79, which is H1 plus 0.84 into HFG, is 2416, and then that gives us 2180.59. So this is H5. Now we can find out the turbine work. Since we know turbine work is equal to m dot into H3 minus H4 plus m dot minus m dot B into H4 minus H5, but turbine work is known to us as 5.6 into 10 to the power 3 kilowatt. Here we are neglecting WP and making it close to 0. So we know m dot is not known, and then H3, we know H3 is the enthalpy at the entry to the steam turbine, 344.3 minus H4, and H4 enthalpy is equal to 2706.7 plus m dot minus now m dot B. We have found out m dot B as 0.528 into H4 2706.7 minus H5 2180.59 is equal to 5.6 into 10 to the power 3. In this equation, only unknown is mass flow rate, which is the total mass flow rate of the steam or mass of flow rate of the steam generated in the boiler. So we can get from here, which is m dot, and m dot comes out to be 4.648 kg per second, which is equal to 16731 kg per hour. So which is equal to 16.73 tons per hour. So this is what we have got from the mass flow rate for the steam power plant, which is used as a cogeneration plant. Now we will go ahead and we have to work for the coal, which is the total fuel supplied for the cycle. So for that we will first find out H7. H7 is equal to H6 plus specific volume at 6 into P7 minus P6, and this turns out to be 508.73, where H6 is at the bleed pressure, which is 2 bar, the liquid saturation enthalpy, and we know this as 504.7 from the steam table. We can also find out H2, which is equal to H1 plus specific volume at 1 into P2 minus P1, and this gives us 153.8, since we know H1 is equal to 149.79 kilojoule per kg. Now this is useful for us to find out the fuel related data. So boiler efficiency is given as 88%, which is basically Q in divided by mass flow rate of fuel into its calorific value, and we had found out Q in. Basically we have to find out Q in over here. So let us find out Q in is basically m dot minus m dot B, which is the mass flow rate of the bleed, and this is the mass of the steam, and this is getting heated from 2 to 3, and then only m dot B gets heated from 7 to 3. It means that the pump actually deals with m dot minus m dot B and supplies to the entry to the boiler. So m dot minus m dot B gets heated in this complete path from 2 to 3, but m dot B joins over here at 7. So m dot B gets heated from 7 to 3. So this is what it is written over here. So from here we get Qn as 15.111 megawatt. So we can put this Q in, and then it becomes 15.111 into 10 to the power 3 divided by mass of fuel into its calorific value, and calorific value is given to us as 25 megajoule per kg. So, this is 25 into 10 to the power 3. So, we get m dot f is equal to the mass of the fuel 0.687 kg per second, which is equal to 2473.2 kg per hour, and which is also equal to 2.47 tons per hour. Now, having solved for the fuel, we have to work for the cooling water which is used in the condenser. So, we are losing the mass, losing the heat, as the mass m minus m dot passes in the condenser from 5 to 1. So, m dot minus m dot b loses its enthalpy from 5 to 1, and then that is used to be a source for the cooling water, where cooling water gets that and gets heated. So, we can know that, and that can be evaluated first, and it will turn out to be 8.367 megawatt. Since we know m dot now, m dot basically we know m dot from here, we know m dot b from earlier calculations of our. So, m dot is known, m dot b is known, h5 is known, and h1 is also known. So, knowing this, we just found out the Q out. So, Q out for us is equal to mass flow rate of water into Cp of water into delta T of water. So, this is equal to 8.367 into 10 to the power 3 kilowatt. So, m dot water into Cp of water is 4.187 into 6 degrees Celsius or Kelvin as rise is equal to 8.367 into 10 to the power 3. So, this gives us mass flow rate of water to be 333.05 kg per second. So, this is how we would have solved the example for the cogeneration plant, where we have to find out the work as electricity output and also the work or the heat transfer in the form of heat load. We would see the rest of the concept in the other classes. Thank you.